Pretty much the first thing you know about calculus is the power rule. In derivatives, we have this formula, which works for all real n. And in integrals, we have to be a lot more careful about the upper and lower limits and n itself. However, instead of using this derivative to prove the following result, we would directly compute the integral considering the area under the related curve. The argument presented here is applicable to all n being an integer, although it can be generalized to n being rational. And of course, the natural logarithm here can give rise to one definition of e that is somewhat more visual than you might have used. Let's say this is the graph of x to the power n, where n is an integer at least 2. Then we consider the area under the curve from A to B, and we approximate the area using these quite interesting rectangular strips. Here, these rectangular strips end in BR, BR squared, BR cubed, and so on. And ultimately, the lower limit A is B times R to the power k, where k is the number of rectangular strips. And the height of each rectangular strip is the function value at the right of the strip. And so, the area can be calculated as the sum of the products of width and length of these rectangular strips. Note that each term has a factor of b to the power n plus 1, and also each term has a factor of 1 minus r. And now, what remains is a geometric sequence. Then by multiplying both numerator and denominator by 1 minus r to the power n plus 1, we note that these two have a simple product. We can simplify this geometric sequence. However, notice what happens when we swap these two factors. Because a is by definition equal to b times r to the power k, these two factors multiply together to b to the power n plus 1 minus a to the power n plus 1. And this is an approximation of the area under the curve. And so, to obtain the actual area, k needs to tend to infinity, or equivalently, r tends to 1. Note that this part is independent of k or r, and so we will ignore this part when we proceed. So here we have this limit to consider. For n an integer at least 1, we can factorize the denominator in this way. And so, the factor 1 minus r can be cancelled, and this limit is equal to 1 over n plus 1, at least for n greater than or equal to 1. You can easily see that it is very clearly also true for n equals 0, and we now need to venture to the negative integers. To do this, we multiply both numerator and denominator by a power of r to make all powers positive, and now we get this fraction. And of course, we do the same algebraic manipulation and get that this limit is also 1 over n plus 1. And it is not difficult to see how you can generalize the factorization process for n being rational instead. And now recall why we have to take the detour. Ultimately, we want to calculate this integral, and this boxed expression is an approximation using k rectangular strips, and hence we need to calculate the limit before. And we have calculated the limit to be 1 over n plus 1, and so we get this power rule. And now the only irritating case is where n equals negative 1, because we would then have denominator to be 0 all the time. But let's see what actually happens to this method of calculating the area. Notice that in all these areas, they are actually the same, all being 1 minus r. The fact that these areas are the same is actually an illustration of the logarithmic property of this area. Why? The ends of these rectangular strips form a geometric sequence, and the corresponding areas under the curve from B would then form an arithmetic sequence because these areas are the same, all being 1 minus r. And logarithms do just that, changing a geometric sequence to an arithmetic sequence. But in any case, let's resume the calculation here. Because there are k rectangular strips, all having the same area of 1 minus r, the total area is k times 1 minus r. And because of this relationship between a and b, we can express r in terms of a, b, and k. Now notice that the only thing that matters is the ratio between a and b. And in fact, the actual area is obtained when k tends to infinity, and is in fact log of b over a. But of course, we need to know the base of the logarithm. Don't worry, because it's just the value of b over a when the area is equal to 1. And we can actually use this as a definition of e. And among the different characterizations of e, this area 1 is actually pretty visual. In the first video in the series doing integrals without integration, we consider rectangular strips of the same width. And I said it is an illustration of Riemann sums. And the method used in this video is also Riemann sums, and this shows the flexibility of using Riemann sums to calculate some integrals without using antiderivatives. This should be really the last video in the series unless there are other ideas that fall into the scope of this series. If you enjoyed this video, give it a thumbs up and share this video. Don't forget to subscribe with notifications on for more of these math videos. See you next time!